So, now we start the periodogram session again. First, we would like to show different kind of windows, and for the different kind of windows, we would like to notice you the forms. The simplest one is the rectangular window, that we have finite amount of data. So, window varies up to that, and then it becomes 0 in either side. So, corresponding to that, the filter we get, that is sinc function, and next comes that Bartlett window. Instead of a rectangle, it is a triangle. We get that at the center it is having the maximum value 1, and both the sides it is coming to slowly reducing linearly, and beyond a point, that value more than m, it will come to 0. Next we get Hanning window. Instead of a linear decrease in the window value, again it is maximum at the middle, and I think few properties are common for all these windows, that they have maximum value at k equal to 0, and they are symmetric, and also they are even function. Okay. So, these properties are common. Now, the first one is having actually 0 slope, the second one having linearly it is decreasing from 0 to, as we move either side, increase the lag. That Hamming window, it is using a cosine function. So, the decrease is following the cosine function, and that cosine we know, when cosine 0 it is 1, and as we increase the angle, the value will decrease. The Hamming window is also very close to Hanning window, only thing the proportion is changed, the DC value and this value, that it is changed. Then the Prasen window, it has a polynomial form of k. Okay. So, these are the different choices of window to actually take care of the side lobes, but the one which gives more attenuation in the side lobe, we need to keep in mind the main lobe width increases for that window more. Among these, if we take the simplest one, that rectangular window, it has actually smallest 3 dB bandwidth, okay, but the attenuation of the side lobe is very small at the same time. So, it has very strong side lobes, that is the demerit of it. Now, as we move forward, we go for the other windows, we get improvement in the suppression of the side lobe, but at the cost of increase in the width of the main lobe. In fact, both has their negative effects. If the two harmonics are there close by, that side lobe frequencies that can accentuate and actually merge them together. Again, if the separation of them is less than the main lobe width, these two can become actually merged, these two harmonics. So, you will not be able to separate two harmonics as a two different one, they would look like one single frequency in the periodogram. Now, let us move forward from here. that we get a dilemma. So far we have found that periodogram makes the life easy and we all use it in real life, but we get to know after taking this previous session that it is not a reliable estimator. Okay. And we gave you the example of white noise to test it out. Now, what is the way out? Can we throw away periodogram and go back to the old classical definition of autocorrelation? May try that, but again the problem does not end, because when we have finite amount of data, how do we get infinite lags of autocorrelation? That is not possible to calculate. Okay. So, we do not have much fallback option. So, we look for the way, explore that how we can move forward, and the solution came as in the form of averaged periodogram. What it suggests that let us take k independent data records and let us compute, first record them, that x 0, x 1, 2 x k minus 1 independent data records, and compute the periodogram of each one of them, and the new periodogram estimate is the average of these individual periodograms. So, that is the new estimate in front of us to take care of the problems generated by the original definition of periodogram. Okay. So, let us see how far that this average periodogram that take care of the problems we had earlier. So, periodogram estimate or the average periodogram we have defined, and for that if we look at that each of the individual component, we get it in this form. That it was like the previous estimate, we are taking just the average of them. Now, let us have some observation out of that. If we take the average, the mean of the average periodogram, it would be same as the mean of the periodogram of the each data set. That means, if we take the expectation of the average periodogram and expectation of the each of the individual that periodogram, they will give us the same value. Okay. So, that is the first observation we get. Next is about the bias. The bias of the average periodogram will be decreased by a factor of k. Here actually we have taken k data sets. So, we get one good thing after taking the average periodogram, that variance is decreased and the property of bias remains to be same, that if more data is there, that we have that less bias, and with increasing the data we were suffering from high variance in the periodogram, and high fluctuations in that frequencies, we can get rid of them or we can suppress them at least, and the decrease would be proportional to the or inversely proportional to the number of such data sets we get. But in real life actually the solution is not so easy. What we really have, that we have one data set, we do not really get actually k independent data sets, but to make them independent as far as possible out of the same data set, what we do, we take k non overlapping blocks, because if we take overlapping blocks, we are straight away contradicting the assumption that they need to be independent. So, we are taking k non overlapping blocks of length L. So, the total data, if it is n, that is equal to k into L. That means, we are utilizing all the data what is given to divide into k subsets or non overlapping subsets. So, in this way that we have generated the individual data sets which are assumed to be independent, at least that is true so long the observations are independent from each other. Now, to get the proper value of L, we take a technique called window closing. Now, what do we mean by window closing? For that we need to go back to the bit of understanding that what is the effect of choice of k and n. We have seen that if we increase the value of k, what will happen? For a fixed n, L will decrease. That means, length of individual data sequence will decrease. What will be the effect of it? We get that if we do that, then we will have actually that band pass filter which comes out of the finite amount of data set. It has a bandwidth that is proportional to the number of data, that is 1 by L in this case. So, frequency domain resolution will decrease if we reduce the L. So, that is not a good option. Again, to increase the L, if we reduce the k, what will happen? Frequency domain resolution will increase, but the variance also will increase in the frequency domain, because the variance is proportional to 1 by k. So, we are in a dilemma. So, what we do really in the window closing method, initially we start with say one sequence of the whole data and we see how the frequency estimate looks like or the PSD looks like. It will give highest amount of frequency resolution, at the same time maximum fluctuations also in the PSD. So, we will get very fluctuating estimate of PSD. So, after that what we do? We keep on increasing the k and thereby as from the value 1 it goes to 2, 3, 4, the L decreases, and we see that how the change takes place in the PSD, and we continue the operation till it becomes smooth. But we do not want the prominent peaks in the PSD that will actually merge together and the PSD will look somewhat different. So, we want to preserve the frequency resolution, at the same time we want it to get smooth or the variance should come down. So, we keep on changing the k till that point and stop there when we see that it has become smooth enough, but the separate peaks they are not got merged. Okay. So, that is the only way, by manually tuning them to go forward to actually change these values and that thereby select the ideal value of k. Now, we get another suggestion that averaged periodogram could not solve our problem. We can actually accept that it is better than the original periodogram, it helps to reduce the variability in the PSD, but it does not completely eliminate the problem. So, these two gentlemen, Blackman and Tukey, they came forward with their analysis and suggestion to give a better solution. So, let us see what is they are offering. First, they point out that what is the cause of the problem, and from there in a very logical way they build up their theory. So, let us look at their proposition. So, the first thing what they have suggested, that periodogram is a poor estimate of PSD and thereby it gives a scope for improvement for Blackman and Tukey. Now, we can have some explanation for them, and for that we need to look back the formulas of periodogram. If we look at the periodogram formula, what we get in the periodogram, what we are actually taking, that is the estimated autocorrelation sequence instead of the autocorrelation sequence. We are taking the Fourier transform of the estimated autocorrelation sequence to get the estimate of the PSD. So, that is the source of the problem, where here is the expression of the autocorrelation function. Here is the function of the autocorrelation, the estimated autocorrelation function from a finite data set. For the positive lags, we have computed them. As the window is changing, what we notice that number of terms is decreasing as the lag is increasing, because the data beyond x n minus 1 is not available. So, that is assumed to be 0. So, even if we write here, it does not make any sense. And for the negative lags, we simply have taken that they are related by a conjugate transposed. So, from that positive terms we can get the negative terms, negative lags. Okay. And for a real data, as conjugation does not make any change. So, it would be just a reflection of the same set of coefficients. Okay. For a complex input data, we will get actually the conjugate, otherwise we will get just the a even function by such estimate. Okay. So, now here let us proceed for the analysis, that the Blackman-Tukey, they suggested that the poor performance of periodogram is due to poor ACF estimator. It is true that we have not taken the ideal estimator, we have taken estimated ACF for doing the job. So, they have suggested that the ACF is the real cause of the trouble, the poor estimate what we have taken for periodogram. And for that they have taken the weakest point of periodogram, they have taken the last lag of ACF. Okay. For that what we get? We get the estimated value is x star 0 into x n minus 1 by n. Now, what is so special about it? Here we do not have any averaging. In fact, we have all the terms to average, that means n terms we had to take average for the lag 0. As we increase the lag, we see the number of terms is reducing linearly, and for the last lag there is no averaging at all. Now, these cost us in terms of fluctuation. If there is no averaging, that estimate what we are taking, the ideally we are supposed to take actually expectation operator of the two terms, okay, that x star n into x n minus k, or you can take the star on the second one, leaving the first one the way it is defined. Now, that expectation was actually replaced by the summation here, using the concept of ergodicity of the sequence, that this is a stationary sequence and that the averaging in the random space can be replaced by the averaging in the time domain. So, that averaging being missing, we have to pay for that penalty and we get high variability in the estimate. And unfortunately, this is going to be there no matter how large is the n. Only thing what will happen, that for that lag, this lag will also change. That means, if the value of n was 10 initially, then we would get the maximum variance at 10th lag. Now, if n becomes 100, we will get that at 100th lag, but qualitatively if we look at that, what is the betterment for the last lag, we cannot say anything positive. Okay. Qualitatively there is no change, this situation would be there, and in this setup we cannot do any change. The mean of the ACF, what we get, it is actually a scaled version of the true value. If we take the expectation on both the sides, that means of the estimated autocorrelation function r hat x x k, we get this expression, this is the true autocorrelation and we get this term, and this is nothing but a actually triangular wave multiplied with the real autocorrelation. Okay. So, we get that there is a bias also is present. By taking the expectation, we are not getting the true value. Okay. So, the mean of the ACF estimator at best we can say equal to the true value weighted by a Bartlett window. Okay. That is the maximum positive we can say. And the first fix that comes to our mind, that what we can do to make it unbiased ACF estimate, we can change actually the formula of the real that estimate of the autocorrelation. Instead of using 1 by n, we can actually modify that. At least we can use the number of terms present in the summation. Okay. And here is the new formula we get, that new estimated autocorrelation we can take as summation of the terms within the given sequence. Please keep in mind, we cannot increase the number of terms here, because we have the value from for x n for n equal to 0 to capital N minus 1. That means n terms are there. There is no way to increase this one. What change we have done? Instead of taking 1 by n, which is insensitive to the fact that number of terms is reducing with increase in the lag, we are taking here the proportionate value here 1 by n minus mod k. That means, how many terms are there? We are scaling in that way, and the relation between the negative lags and the positive lags remains the same. There is no change there. Okay. So, that at least we hope can take care of that fact that we would not have the extra term here what we are getting in this form, that Bartlett window, that would be eliminated. Okay. So, that is the expectation. So, if we can do it in this way. Now, let us see what we get, that in this way that the choice of unbiased ACF estimate, we made the estimate of ACF unbiased, but it gives rise to another problem, that it can give negative spectral estimate, as this new unbiased ACF estimator does not guarantee a positive semi definite sequence. So, what we mean by that, that as this is not a positive semi definite sequence, if we take the Fourier transform and take the absolute value may become negative. Now, what is the problem with that? The problem is, we are talking about the energy of a signal, and energy cannot be negative. If we get a negative spectral estimate, we are unable to explain that how the energy becomes negative. So, we wanted to do something very positive, we wanted to fix the problem of bias, but it has come out in a new way, which is again detrimental to the performance of the estimator. So, let us look forward, let us see that what alternatives can be made. In fact, Blackman Tukey, they suggested these alternatives. So, we can take that these are the new propositions of Blackman Tukey here. What he suggested, or rather what they suggested, that the main problem is in the poor ACF estimate at high lags due to fewer number of lag products for averaging. The higher the value of lag, we have less terms for them and we get more and more poor estimate of the ACF when you go for higher lag because of lack of averaging. So, we need to think from that angle and do something. So, one way is to give less weights to the ACFs at high lag. It is very reasonable kind of assumption that where we have less confidence, let us use less percentage of information from there. Okay. So, that is the thing Blackman and Tukey suggested, and for that what they have told, let us take the estimate of estimated autocorrelation function as we take in the case of periodogram and apply a window. Earlier we have introduced you with number of windows. So, they gave a actually solid footing for them that why they should be there. Let us take a window multiplied with the estimated autocorrelation estimate with the purpose to actually give proper weighting to the different lags of autocorrelation function. We know near the center that autocorrelation function estimates are better and they become more and more unreliable as we move away from the 0th lag. So, W, the windowing function, should actually look at that phenomena and take appropriate action for them. So, they should have some property. First of all, that for different lags, that the first property would be that W0 should be maximum, that is equal to 1, and window should be positive, because we do not want to change the sign of that autocorrelation estimate. So, all the other lags, the value should be in between 0 to 1. Next, that as the autocorrelation estimates are even for the real data, same would be true for the window. So, it should be a even function. Okay. Third thing is that it should go to 0 beyond some m. What should be the value of m? M should be less than n minus 1. That means, we could compute actually the lags up to n minus n, autocorrelation up to this point, but we know when we go near to n minus 1, the number of terms to average would be very less. In fact, there would be only one term at n minus 1th lag. So, we need to get rid of that situation. We should stop it much before that, we should stop it at some value m. Beyond that, we know the estimates are so unreliable, there is no point in using them. Okay? Because if we try to take them, we may have more noise rather than real input. So, we curtail that, we use only the central portion of the estimates and weight them to give maximum weight to the 0th lag, and for the other lags we are giving some appropriate weights, and that window should be a even window. Now, let us move forward. Using the last property of this window lag, now the periodogram estimates, it gets a new form, where instead of taking the value of k minus n minus 1 minus n plus 1 to n minus 1, we restrict it from minus m to plus m, or using less number of lags. And this is what is called as Blackman 2K spectral estimator. This is what they proposed. And there is also another term, it is called weighted covariance estimator, because they have suggested a weight to that autocorrelation function. Okay. So, this was the proposition of Blackman 2K, and we will stop here for this session. Thank you.